Hello, welcome to the seminar presentation on Engineering Scalable Systems, the core principles of LLD and Solid, presented by myself, Prabhu Teja Pamula, 24EMCA1237, and my seminar guide is Dr. Brijendra Singh, Professor. The outline Phase 1 Architectural Assessment and Problem Domain. The phenomena of software rot, degradation metrics in production environments. Structural code failures, mechanics of fragility, rigidity, and high coupling cascading. System boundaries, delineating high level design, HLD, topology from low level design, LLD components. And phase 2, foundation layer, the OOP to solid transition. The paradox of object oriented programming, how misused inheritance and encapsulations drive rigidity, design smells, technical indicators of component inelasticity and immobility. Phase 3 The Solid Engineering Framework, Single Responsible Principle SRP, designing high cohesion and single reason to change, open and closed principle OCP, abstraction layers and extension vectors. Likosvy's substitution principle, LSP, subtyping contracts and behavior invariance, interface segregation principle, ISP, lean contracts versus fat interface anti-patterns, dependency inversion principle, DIP, component decoupling and dependency injection mechanisms. Phase 4, design principles and real-world validation. Creational blueprints, the factory method implementation logic and object instantiation decoupling, behavioral blueprints, strategy pattern for runtime algorithm interchangeability, enterprise case study, bringing academic MCA coding to production ready systems, seminar synthesis, key technical takeaway, and reference verification. These are the outlines. Now let's start with phase 1, architectural assessment and problem domain. The phenomena of software rot, the working code trap. Just because code compiles and passes its current test does not mean it is high quality. Real success means the code is clean enough for another developer to safely modify it next month without triggering unexpected system failures. Focusing only on quick results creates hidden traps that make future development impossible. Why code automatically rots? Tight deadlines and pressure forces developers to write quickly, messy fixes rather than clean architectures. Skipping proper low level design blueprints causes code quality to drop continuously over time. Rushing a feature out the door without refactoring leaves behind permanent structural flaws. Understanding technical depth. Technical depth is the long term cost of taking shortcuts and writing messy codes to hit a fast deadline. It acts like a financial debt. You get a quick release today, but you have to pay interest later through constant bugs and slower development speed. If a team ignores this depth and never refactors the code base eventually becomes too expensive and broke to maintain. Visible signs of rotting code. Simple updates that used to take few hours now take days or weeks or manual troubleshooting. The system becomes highly fragile. Patching a single bug instantly creates multiple new errors across unrelated modules. Engineering teams spend almost all of their working hours fighting critical production fires instead of building valuable new features. Structural code failures. The reality of rigidity. Rigidity occurs when a code base becomes entirely stiff and heavily resists everyday update or logic modifications. When an engineer attempts to execute a simple feature change in one localized file, it triggers a ripple effect, forcing manual code rewrites across multiple dependent modules. This design failure severely damages development velocity because minor tasks require hours or days of unnecessary exhausting refactoring. The threat of fragility. Fragility describes a highly unstable production system that fractures easily whenever a code modifications are deployed. When a small isolated bug patch is applied to a single component, it unexpectedly disables completely unrelated functional areas deep inside the platform layout. This forces engineering teams into a defensive position where they feel like they're constantly walking on eggshells during every release window. The high coupling cascade. High coupling represents the structural architectural failure that acts as the direct root cause behind both rigidity and fragility. This degradation takes place when concrete objects or classes contain intimate hard-coded dependencies regarding the internal mechanisms of neighboring components. Instead of functioning like loose, interchangeable Lego blocks that support clean upgrades, the system modules operate as an inseparable permanent glued mass. System boundaries, HLD versus LLD. The macro architecture versus micro component boundary. High level design, HLD, acts as the comprehensive micro map of the system, defining where major infrastructure assets sit across the network topology. Low level design, LLD, serves as the precise logical blueprint of an individual code module outlining class interactions and code level component relationships, establishing a clean, distinct boundaries between two domains ensures infrastructure scaling decisions remain decoupled from day to day code modifications. Infrastructure topology and global routing data HLD dictates the macro level engineering environment, including the selection of enterprise relational or non relational database engines, establishes load balancing algorithms, API, API gateway, in- ingress controls, cloud server clusters configurations, and physical data center routing strategies. Manages how independent software systems, external microservices, and third party APIs transmit massive data streams across the network layers safely. Component level mechanics and code governance LLE operates entirely at micro level, defining exactly how engineers write clean, maintainable, object-oriented programming files, establishes the exact communication boundaries between concrete classes, public interfaces, abstractions, and data transfer objects, enforces strict object-oriented design patterns and creational strategies, allowing specific code modules to accept new business features without risking system crashes. The interdependency thresholds and system viability. High level design proves that scalable hosting environments to process user requests, while low level design ensures code remains financially maintainable over time. Without robust LLD governance, code complexity grows exponentially, eventually leading to cascading software decay that halts new software features entirely. Even if a company invests in highly expensive cloud server architecture, the overall platform will crash if the underlying code is allowed to rot into a unmanageable mess. Phase 2, the foundational layer, the OOP to solid transition. The paradox of OOP, the trap, the semantic misuse of inheritance, the misconception of code reuse. Most developers mistakenly use inheritance as a shortcut for code reuse rather than representing a strict logical is a relationship. Implementation binding. This binds the child class to the physical implementation details of the parent, violating the principles of local reasoning. Architectural stagnation. Because the subclass is now a slave to parent's logic, the system loses the ability to evolve component independently. The problem, the fragile base class cascade, deep hierarchical vu- vulnerability, creating deep inheritance tree. Parent is greater than child and then grandchild, introduces the fragile base class problem into the architecture. The rippling effect, a minor seemingly safe modification into the root parent class triggers a destructive regression cascade through dozens of dissonant classes. The birth of rigidity. This is precisely how rigidity is born. Engineering become Engineers become afraid to touch core classes because they cannot predict which leaf class will crash. Encapsulation failure, the getters setters anti pattern. Pseudo encapsulation. Simply hiding variables but providing public getters and setters for everything is not true encapsulation. It is a data leak. Anemic domain models. This creates dumb data classes where logic is separated from data, allowing external modules to bind directly into internal structures. The loss of integrity. Every external class becomes dependent on internal state of the object, making it impossible to change the data structure without breaking the entire system. Design smells. The concept of architectural design smells. A design smell is not an active execution bug or a production error. Instead, it represents a structural symptom indicating that the underlying architecture is actively rotting. It acts as an early warning matrix for software engineers, signaling that while the system currently passes its test, future logic updates will become drastically harder to implement safely. In elasticity, structural rigidity, and resistance to change. Interelasticity occurs when a code becomes entirely stiff and fails to bend or adapt gracefully to changing software requirements. When a developer attempts to stretch the current system framework to integrate a new business feature, the rigidity dependency like snap, creating critical regressions errors. Immobility, the inability to reuse system modules. Immobility describes a failure state where highly valuable modules such as login or authentication component cannot be shared or reused in separate company projects. Because the module is tightly glued to local database configuration and specific logging engine, reusing it requires copy pasting massive chunks of irrelevant bloated infrastructure logic alongside it. Viscosity, the path of least resistance versus design governance. Viscosity measures how difficult it is for a software engineer to do the right thing versus executing a dangerous shortcut. When a system exhibits highly viscosity, it is physically easier and faster for a developer to implement a sloppy hacky fix that is easy to preserve and follow formal clean architectural pattern. Phase 3, Solid Engineering Framework. Introduction to Solid Principles. The architectural evolution, component governance. Base Object Oriented Programming, OOP, only offers elementary structural components like classes, interfaces, polymorphism, and encapsulation. Crucially, raw OOP provides no standard governance rule on how to assemble these components safely. Solid provides that necessity governance framework. The core architectural objective. The primary objective of the solid framework is to structurally limit the blast radius of day to day software code modifications. Implementing these patterns ensure that a future update or bug patch made to one localized system module never ripples outward to break completely unrelated features. The return on investment ROI stability curve. Ungoverned software suffers from an exponential cost of change curve, meaning updates become drastically slower and more expensive over the life cycle. Adhering to solid straightens the trajectory into a predictable linear pace, protecting long-term development velocity. Single responsibility principle, the formal definition. Actor driven responsibility. Robin C. Martin, Uncle Bob, defines SRP strictly around business stakeholders. A module should not be responsible to one and only one actor. A module should be responsible to one and only one actor. Defining the actor. An actor represents a specific group of stakeholders, such as finance, HRs, or DBA, who possesses unique business requirements and can independently request a code change. Reason for change: the single pivot metric. SRP is not about a class performing only one functional task. It dictates that a class must possess a single, isolated reason to change. The multi actor violation. If a single class serves multiple actors simultaneously, it creates a severe architectural violation trying independent business workflows to the same file. The benefit: maximizing high cohesion, isolating distant responsibilities into separate classes creates highly cohesive modules that are simpler to maintain. Blast radius protection. This decoupling prevents a change request by the finance department, like updating a tax calculation for academically for accidentally breaking completely unrelated reporting code used by HR department. Open and close principle. The code definition. Mayer's architectural axioms. Bertrand Mayer defines OCP, stating that software entities like classes, modules, and functions must be open for extensions but closed for modifications. The stability goal. This foundational concept ensures that the core system features remain completely stable and trusted while allowing the applications to support new business requirements over time. Closed for modification. Production integrity enforces once a core class is written, unit tested, and compiled into production, its existing code base should never be touched or altered to implement new feature. Regression protection. Lock down existing code mechanics to insulate tested business operational business logic for the accidental introduction of unexpected regression defects. Open for extension. Scale through addition introduces new system behavior and features exclusively by creating new subclasses for implementing existing interfaces. The new code metric scales systems capabilities dynamically by writing entirely new isolated files, completely eliminating the need to rewrite or alter old existing code blocks. The architectural mechanism polymorphic inversion. This pattern relies entirely on core polymorphism and abstraction layer to decouple the execution flow cleanly. Stable contracts. The calling context depends on executively on stable public interface contract, allowing brand new implementation features to plug directly into the interface layers seamlessly. Liskov substitution principle, the Pommel definition, subtype substitutability. Barbara Liskov defines it as a subtypes must be substitutable for their base type without altering the correctness of the program. The core requirement: a client program must be able to pass any class variant into a function without knowing its specific implementation type and without causing a crash. The behavioral contract. Honoring parent behavior. Inheriting from a parent class means you must honor behavioral expectations. A subclass cannot arbitrarily choose to reject or break a method inherited from its parent. The failure state, subtype volatility, runtime exceptions. If a subclass throws an unexpected runtime error, like an unsupported operation exception for an inherited method, it breaks the parent's contract. The client breakage. The client expects the inherent behavior to execute smoothly. Forcing it to deal with a broken implementation means LSP is violated. The classic word violation, the ostrich dilemma. The flawed assumption. Assuming all birds can fly lead to putting a fly method into a generic bird-based class. The contract breach. When an ostrich subclass inherits from the base class, it cannot behaviorally implement fly method. It is forced to throw a runtime error, breaking the exceptions of any module handling generic birds. Interface segregation principle. The code definition. The client-centric rule. Clients should not be forced to depend upon interfaces that they do not use. Eliminating bloat. This principle focuses on designing thin, role specific interfaces rather than forcing implementing class to inherit behavior they do not require. The problem: fat interfaces. Monolithic abstractions. When an interface grows too large, it accumulates methods that serve completely different client requirements. Boilerplate pollution. Any class implementing a fat interface is forced to write user boilerplate implementations, often throwing a runtime not implemented exceptions or returning null for unsupported operations. The structural harm. Compile time coupling. Fat interfaces create unnecessary compile time dependency across the system architecture. The recompilation cascade. If you modify a single method header used only by client A, every single other client class in the code base is forced to recompile completely, destroying component isolation. The solution: role-based segregation. Split fact interfaces into small, highly cohesive, specialized contracts based on client actual usage domain. Decoupled architecture. Classes should implement multiple small interfaces instead of one giant interface, ensuring changes to one capability never ripple into an unrelated system module. Dependency inversion principle. The code definition. Martin's decoupling mandate. Robert C. Martin dictates two structural laws for DIP. High level module must not depend on low level module. Both must depend strictly on abstractions. Details independence. Abstraction must never be depend on volatile concrete details. Instead of low level concrete details, must depend entirely upon high level abstractions. The traditional flow of control. The trap. The hard coding vulnerability. In traditional procedural or unmanaged object oriented code, high level businesses policies classes directly instantiate low level utility components. Structural fragility. Directly hard coding a production dependency such as locking a notification service to a specific MySQL database instance renders core business logic fragile and vulnerable to downstream infrastructural changes. Inverting the dependency, bypassing direct links, inserting an explicit abstraction layer interface between components completely breaks the rigid compile time coupling. Inverting system controls. The high level policy module assumes complete control over the shape, signature, and contract of the interface, forcing all low level operational modules to conform to it. The architectural value. Establishing pluggability. This inversion establishes a highly modular, pluggable application architecture across the enterprise. Insulating core logic. Engineering teams can cleanly hot swap underlying databases, switch third party communication APIs, or replace logging frameworks without modifying a single line of core business policy logic. Phase 4: Design patterns and real world validation. Creational blueprints. The problem: the new keyword violation. When you use the new keyword to instantiate a concrete subclass directly inside a client class, you break the dependency inversion principle, DIP. This direct instantiation tightly couples high level modules to low level implementation details, making it impossible to swap out components cleanly. The factory remedy. The factory method pattern decouples object creations by abstracting the instantiation process away from the client class. Client code only interacts with a generic stable interface, while a dedicated factory subclass encapsulates and handles the actual concrete object creation behind the scenes. The operational value. To introduce a brand new concrete type to the system, you simply write a new class file and plug it into the factory structure. The existing client code remains completely untouched and closed for modification. satisfying the open closed principle OCP while scaling application features. Behavioral blueprints. The problem, the open closed violation. When runtime behavioral algorithms are hard coded inside massive conditional blocks like if else or switch statements, the system architecture becomes brittle. Adding a new business rule forces you to modify the existing host class, violating the open closed principle OCP and risking regression bugs in stable production code. The strategy remedy, polymorphic delegation. The strategy pattern defines a family of algorithms, encapsulate each one inside its own dedicated class configuration, and makes them fully interchangeable. By shifting logic from hard coded switch cases into independent strategy classes, the system relies on a shared interface contract to delegate execution at runtime. The operational value, zero modification scaling. The host execution context remains entirely decoupled from specific runtime implementation variants. To add a new algorithm or business rule, you must simply create a new strategy class without rewriting a single line of your core logic OCP, ensuring seamless horizontal scalability. Enterprise case studies. The industrial transition from academic to enterprise. This phase represents the critical shift from a single file academic code submission towards professional modular architectures designed for multi years life cycles. Architecture for longevity. Professional engineers prioritize infrastructural agility, ensuring that the code base can survive shift in technology stack, team rotations, and evolving business requirements. Quantifiable maintenance ROI, reducing technical entropy. A real world software metrics confirms that wrapping tightly coupled legal systems in solid compliant boundaries can reduce downstream maintenance overhead and bug destiny by up to 60%. The cost of rigidity. By isolating violate components, enterprises avoids the refactoring depth that typically consumes 70% of an average IT department's budget. The hybrid migration strategy. Isolating technical depth, avoiding high risk full system rewrites that often lead to project failure. Instead of stabilizing production platform by deploying specialized adapter and facade patterns, legacy encapsulation. These patterns act as a protective layer, isolating legacy technical depth behind stable, modern interfaces, allowing new features to build with clean decoupling logic with old system continues to run. Seminar synthesis. The architectural shift. Deterministic design. Solid design principles systematically turn unpredictable, fragile code bases into deterministic, highly adaptable enterprise software environments. The governance layer. Non negotiable rules. Software design principles are not optional, stylish choices. They are crucial engineering laws required to control the long term compounding cost of code changes. The final takeaway: clean boundaries, clean architectural separates core high level business rules from violate low level implementation details. The continuous growth metrics. This separates guarantees that software remains open for business, scaling, and rapid future growth, but strictly closed to unexpected regression failures. And thank you.